Hi everyone, I'm Tanika. I work as a principal data scientist at Sigmoid. And today I'm going to cover the topic convolution neural network. So architecture of a CNN is analogous to human brain. So if you think about computer vision is basically an amalgamation of machine learning, AI, and images and videos. What basically a CNN does is that it assigns importance to an input image. Why? And this helps us to actually differentiate one image from the other. In this particular diagram, you can see the architecture of a convolution neural network. We have an input image which goes into a convolution layer, which is followed by a ReLu activation function. This is followed by a pooling layer. So we have multiple convolutional layers and pooling layers, and the final output from all these layers goes into a flattening layer. Now this flattening layer produces the output into a vector form, which is then passed on to a fully connected layer. And finally, we have a soft-max activation function, which gives us the output in the form of probabilities. Now let's look at the first part, which is the convolution. So if you remember, in mathematics, whenever we have two functions which basically are multiplied or combined together to produce a third function, this whole process was called as convolution. Similarly, over here, what we do is that we have an input image. We multiply it with a kernel or a filter, and with that we get a feature map. So for example, in this particular, if you look at the video, right, we have a 5x5 matrix, and now that is multiplied with a feature of 3x3 size, and finally we get a feature map of 3x3. So as you can see that the formula for this is the size of the input image, which is 5, minus the size of the kernel, which is 3, plus 1. So which is 5 minus 3 plus 1, which is 2 plus 1 is 3, and that is how you get a feature map of 3x3. Now, the way we use convolution is that we use it to detect edges, or we can actually use it to blur or enhance the edges. So and all this can be done by using different feature maps, by using different kernels or filters. So based on your filter, you can actually enhance or blur the parts of the image and get a feature map. So this is all for today. I will see you in the next video. Thank you. Hi everyone. Welcome back to session 2 of CNN. Today, we are going to cover the topic of padding and stride. So in the last video, we covered the concept of convolution, where we multiplied a matrix image in the form of a matrix with a kernel to get a feature map. Now in this particular video, we would go further into convolution and cover the concepts of padding and stride. Now we'll cover the concept of padding. So in our last section, we understood the concept of convolution, where we multiplied a feature image with a kernel to get a feature map. Now, so for example, we have a 4x4 matrix, and we multiply it with a kernel of size 2x2. Now, what would be the size of our feature map? It would be n minus k plus 1. So in this example, it becomes 4 minus 2 plus 1, which is 3. So we get a 3x3 matrix. Now, just imagine a scenario where we want, instead of 3x3, a matrix of size 5x5. So what should we do? In that scenario, what we do is the concept of padding. We add a layer on the top, as well as we add a column on the left and right. So our matrix, which was of size 4 cross 4, becomes of size 6 cross 6. And we already have a kernel of size 2 cross 2. So our final matrix becomes of size 6 minus 2 plus 1, which is 5 cross 5. So our final feature map is of size 5 cross 5. So this is the concept of padding. Now let's look at the concept of max pooling and ReLu. So once we have done padding and stride, next we have an activation unit. Post the convolution, we have an activation unit which is called ReLu. So this is mainly deployed to account for non-linear relationships in the neural network. So ReLu is rectified linear unit. Now, post going through a ReLu activation function, we have a max pooling layer. Now, pooling layer operates on each feature map independently. What it does is that it reduces the resolution of the feature map by reducing the height and width of each feature map, but it retains the features of the map required for classification. So this is called a concept of downsampling. Now, let's look at, supposedly we have a feature map. Okay, so this is our feature map, where I'm just randomly putting some numbers. Now, what will happen if we in max pooling is that we will have a 2 cross 2 filter which we will pass along. So we will. So if you look at the first filter, the maximum is 7. So we will put a value of 7. Now in next, we have a value of 3. So we will put a value of 3 over here. Seven, 3. And then in the next, if we go to the next set, we have a value of 5. So we will write down a value of 5. And over here, again, we have a max value of 7. So we will add a value of 7. And now interestingly, over here, we don't have the full. So we'll just take 2 of these inputs because we don't have the next 2, and the max is 1. And in the second one, it's 0. So we'll put a value of 1 and 0. So as you can see, this is a pooled feature map. So what we have done is that we have reduced the height and the width of our original feature map and only retained the important values. So this is important because this helps. So supposedly you have an image which is rotated or zoomed. In those scenarios, if you want your CNN to be able to differentiate between these different kind of scenarios, it's important that it only focuses on the pooled feature, which are the important features, and not be worried about the features which are not so important. So that's why we have this concept of max pooling. Thank you everyone. Hope you enjoyed this session, and I'll see you in the next and final session next time. Thank you. Hi everyone. Welcome to the third session of Convolution Neural Network. In this, we will cover the topic of flattening, fully connected layer, and softmax activation function. In the last video, we understood the concept of max pooling. After max pooling, our input is passed on to a flattening layer. Now, what does flattening layer do? Is that it converts the pooled feature map into a vector form, and this vector is then further passed on into a fully connected layer. Now, fully connected layer is a regular neural network where all the neurons are connected to each other. Now, what happens is that all the inputs from a particular layer are connected to every activation unit in the next layer. So that is why it is called a fully connected layer. But because of this, there are chances of overfitting. And to tackle that, we have a concept called dropout, which is basically a regularization methodology in neural networks. And in that, what we do is that we randomly select certain nodes which are to be ignored in the training phase. So generally, we keep a dropout value of 0.5. Now, post your fully passing through the fully connected layer, the final is the soft-max layer, where we have a soft-max activation function. Now, what soft-max activation function do is that it takes the output from the last layer and convert it into probabilities. So what it does is that we have multiple classes. So every class gets a certain probability, and all of them sum up to 1. Now, what it helps us is that once we give an input image, we get a probability of each class, and this helps us to identify what does that image mean based on the highest probability to the class which it assigns to. I hope you enjoyed the CNN sessions. Please do let us know your thoughts, and if you have any questions, do write it down in the comment section below. And I hope to see you in future sessions as well. Thank you so much.